so the first thing that we're going to talk about in 2.4 is some extra postulates, theorems, definitions that we can use in our proofs. We're going to use all of those properties that we had before, but we're going to add on like 5 more today and then a couple more tomorrow. So for today, we're adding on, number 1 is the segment addition postulate. I'm going to draw us a little tiny diagram here to kind of understand what's going on. But the segment addition postulate, at its most basic form, all it says is that I can add 2 segments together to get the total of one whole segment. So if I have something like this, where they're all 3 on the same line, and B is in the middle, then it literally says that I can add part 1, AB, plus part 2, BC, to get the entire thing, AC. I'm not telling you anything crazy here, right? We know that. We understand that as a concept. We did that in Unit 1. I can add a bunch of different parts in here. Like if I wanted to put in a D as well, I could do that. I could say, okay, AC is equal to AD plus DB plus BC. 3 parts could make up a segment. Doesn't really matter as long as we know that the parts of a segment equal the whole thing. That's the segment addition postulate. Anytime we're adding segments together, that's what we call it. We have a couple definitions. We've seen these words before, but in a proof, we use this like kind of formal way to say the definition of a midpoint. Literally says, here's our biconditional that we learned earlier. It says M is the midpoint of AB if and only if AB equals MB. Actually, I think this is supposed to say AM. So if I have a segment, AB, M is the midpoint if and only if these 2 pieces are congruent. Or vice versa, if those 2 pieces are congruent, then we know M is the midpoint. Similar to that, I have the definition of a segment bisector. The definition of a segment bisector is kind of like a midpoint, except instead of a point, we know that a segment bisector is like a line or a ray. So if I have AB being bisected by CD at point P, all that says to me is that by the definition of what a bisector is, AP is congruent to PB. We've seen bisectors though, right? We kind of understand that concept from Unit 1. Then I can do kind of the same stuff with angles. So similar to the segment addition postulate, I have a angle addition postulate, and that literally says that if I have a whole angle ABC, how can I write this over here? If I have this angle ABC, and then somewhere inside of that angle, I have another ray. Like, let's put it over here. BD. Oops. Then just like we said with the segments, 2 parts make up a whole angle. So these 2 parts, ABD plus DBC, together make the whole thing, ABC. Does that make sense? Okay. I could do that with more than one angle too if I wanted to, but for the most part, you'll see it with 2. And then the last definition that we're going to add in here is the definition of an angle bisector, very similar to the definition of a segment bisector, except with angles. The definition of an angle bisector says if I have angle ABC, here's my conditional, BD bisects ABC if and only if the 2 halves of my angle are congruent. So BD right there is a bisector if these guys are congruent, and vice versa. If those guys are congruent, then we know that BD is a bisector. Okay. Please don't forget these. Give them a star, give them a whatever, a box if you have to. We are going to be using these today and throughout the unit. Let's get into our first real proof. The first proof we're going to do is algebra. Okay, I'm not throwing any geometry at you. I just want to think algebra first. When I look at a proof, the first thing that I'm going to see is what we call the given statement. The given statement is just like whatever information I'm provided at the top. That given statement is, I would say 95% of the time, going to be the very first step in my proof. Wherever we see that statement, we're always going to provide a reason for why that statement is true. Our given statement's reason will always just be the word given. Oh my gosh. So that's kind of like a freebie for us because given is always given. Another thing that will always be true in a proof is that we are trying to, well, as the name says, we're trying to prove something. Our proof statement tells us where we're going to end up. So my very last step should be identical to that prove statement. I don't know what the reason for that is going to be yet. I'm going to have to work through the steps to figure it out, but I know that's going to be my last step. Those should be like freebies at the start of every proof that we do. We should be able to find the givens. We should be able to find the prove statement. Questions so far? Let's just like literally think about this as an algebra problem. I see the statement 5x minus 12 equals 32 plus x. I'm assuming I'm trying to solve for x. What would be my first step here? Algebraically. Algebra problem. Caitlin. Yeah, add 12 to both sides. That's all I'm doing here. But I'm now going to give it a name. In geometry, what do we call that? If I can add it to both sides and still have the same value, it's still equal. What did we call that? Adding something to both sides, Casper? The addition property of equality. So I'm doing that algebra. I'm just giving it a little bit of a name. Not algebra, addition. Addition property of equality. That's all I did. What did I do in the next step? Casper? Subtract x from both sides. So that must be the subtraction property of equality. Then what did I do? From step 3 to step 4. Casper? If I'm dividing by something on both sides, that's my division property of equality. Baby's first proof. We did it. Questions on that? Okay. So most of the ones on your homework, I think actually all the ones on today's homework, have the statements written for you. Sometimes they are not written for you, like we will see in the future. But in number 2, it says, given 12 equals 3 times x plus 5 minus 6, prove x equals 1. There's a couple freebies that I can get every single time. I know that my given statement, 95% of the time, is going to go first. So let's put that first. I have my statement. And then the reason that I can put that there, my justification, one word, given. My other freebie is that I know my prove statement is going to go in my last spot. X equals 1. I don't exactly know why it's there yet. I don't have a reason, but I can definitely put that statement there. Okay, questions right now. This is another algebra proof. So think algebraically. If I were to solve this problem, what would be my first step? Casper? Okay, we can add 6 to both sides. Actually, can we do something else first? Dahlia? Not divide by 3. What do I want to do, Gabby? Yeah, let's distribute first. I think this is going to make it a little bit easier. So let's distribute first. Oops. 12 equals 3x plus 15 minus 6. Our reason, why do we know we can distribute? The property of the same name is the distributive property. Then what would I do here? After I distributed, I want to simplify a little bit, Ian. Yeah, I'm going to combine like terms. I'm going to put together the 15 and the negative 6. 12 equals 3x plus 9. The reason I can do that, my combining like terms property, is just called simplify. Then what? What would step 4 be? Caitlin? We subtract 9 from both sides to get 3 equals 3x. And then one more step here. Anna. Perfect. So I'm left with 1 equals x, and that's the division property of equality. Okay. My final answer here at 1 equals x doesn't quite look like x equals 1, so I have to do something to it to get it to look exactly the same. What did I do to it? What property is that? Casper? Yeah, symmetric. It says that I can flip it. I can mirror that. 1 equals x is the same as x equals 1. That's my symmetric property of equality. That's kind of a nitpicky thing, but our prove statement has to look exactly like the prove statement at the beginning of our problem. So kind of a weird extra little step that we don't think about in algebra, but we have to think about in geometry. Questions on this? We just wrote a full proof, like all the whole thing, right? Let's do a little bit of geometry. Okay, here's kind of what a geometry proof looks like. A lot of the times we get a diagram for us. We have a bunch of given statements, and we're proving that x equals 2. So let's get my freebies out of the way. Here's my given statement. There it is in step 1. I know my reason is one word, given. What else can I put in there for a freebie? Casper? X equals 2. Putting it right down at the bottom. I don't know why yet, but I know that it goes in there. Okay. When we have geometry proofs, the first thing that I do is mark up my diagram. And if I don't have a diagram, I'm going to draw a diagram. So I do have one here, so I'm going to mark it. I'm going to use my givens, which say that AB is 15 minus x. Oh gosh. BC is 4 plus 2x. And then AC, this entire length, is 21. All that I got from my givens. Now that my diagram is marked up, I can start looking at this problem. It gave me a statement in number 2. It says AB plus BC equals AC. Why do I know that is true? What justification do I have for that? I'm not just making that up. Why do I know that? Look at those definitions and those postulates and all that good stuff that we learned right at the beginning of these notes. Ian?
Segment addition postulate?
Yeah, segment addition postulate. This is a super common, like what a statement would look like for segment addition postulate. It says segment plus segment equals segment. I can look at my diagram. Part 1 plus part 2 equals the whole thing AC. Anytime I see that, whether it's 2 pieces, 3 pieces, 4 pieces, always segment addition postulate. Another thing that I want to point out here is that step 1 and step 2 don't necessarily like go in chronological order. Like what we saw in all of our algebra, those were all very much like one step comes after the other. Step 1 has nothing necessarily to do with step 2. We just got to put those in there to get to the next thing. So step 3, if I was thinking about this in like unit 1, what would I have to do to solve this for x? Casper. Substitute the values. So I'm going to take my value for AB, which is 15 minus x. I'm going to take my value for BC, which is 4 plus 2x, equals my value for AC, which is 21. And I can do that because of the substitution property of equality. What would be my next step? Gabby. Simplify, combine like terms. I have like terms 15 and 4. I have like terms negative x and 2x. And we can do combining like terms because of simplify. And then how do I get to my last step? How do I get x equals 2? Casper? Yeah, subtracted 19 from both sides. Subtraction, property of equality. Not too terrible. Everybody's still okay? Okay, move on. Next page. I got to point out a couple weird things here. Number 4, excuse me. So in number 4, it says D is the midpoint of CE, E is the midpoint of DF. What I recommend to you, because we have these weird cases where it's not always the same every single time, what I recommend to you every single time is that you look for those givens first. Sometimes the givens try to hide from us. So my first given is that D is the midpoint of CE. That is where I expect it to be, in the first spot. So I know that I can mark that as given. But sometimes, like I said, 95% of the time it's just that first statement, but that extra 5% of the time, we have another given hiding somewhere else in our problem. So it says E is the midpoint of DF. That's hiding over here in step 3. It happens way more often than I would like to admit that sometimes we look at a problem and I can stare at number 3 for as long as I possibly can, and I still have no idea where I got that information from, when it's really just been a hidden given the entire time. So just do that first, right? Get those out of the way. I see my proof statement is where it's supposed to be. That's already written for me. And now I got to look at, well, how do I know step 2 and step 4 here? Anytime I see a vocab word in a proof, like midpoint, my first instinct is I probably have to figure out what the definition of that word is. So if D is the midpoint of CE, then it could be said that by the definition of midpoint, these two pieces must be congruent. So that's number 2. On that same idea, if I'm saying E is the midpoint of DF, here's E. Again, that word midpoint tells me I'm probably going to have to define that midpoint. So by definition, DE is congruent to EF. So anytime we see those words, midpoint, bisector, we'll have more in the future. But those are telling me I'm probably needing a definition there. How do we get to step 5? Had to put a couple things together here. How did I get to step 5, do we think? Caitlin? Exactly. CD is congruent to DE. DE is congruent to EF. I can cut out that middle part and just say that CD is congruent to EF by the transitive property of congruence. Questions on that? I'm going to rapid fire through this one a little bit. I got my givens, I got my proof statement. I'm trying to prove that x equals 20. I see a diagram. It's got some stuff in the diagram as well. I'm looking at number 1. My statement is that ray LM bisects KLN. What's my reason there? Given. That's a freebie, right? Number 2, the measure of MLN equals the measure of KLM. Definition of what? You see this word here? Oops. It's not segments. What am I looking at in this picture? Angles. So I saw that word bisects, right? Bisects tells me I'm probably going to have to use the definition of an angle bisector. Then how do I know number 3? Caitlin? Perfect. I'm taking these values from my diagram and I'm substituting them in. Number 4, how'd I get there? Anna? Subtract 2x from both sides. And then how'd I get to my last step? Caitlin? Perfect. Are we feeling okay with this right now? I'm going to give us a little brain break from proofs, and we're going to do system of equations real quick here, and then I'll let you go. Okay, systems of equations. Remember, we're going to have more than one variable in our equation, so we're going to have to solve this using substitution or elimination, something like that. Let's first set up our equations. We need 2 equations here. How can I relate these variables in some equations? What do I know about this diagram? Uh-oh. I had some definitions and stuff. Caitlin?
4y plus 2x is 180.
Perfect. Linear pair. They make a straight line. So these 2 angles together make 180. That's a linear pair. So I can say 4y plus 2x equals 180. Can't really do anything with that yet because I've got 2 different variables. So I need another equation. What's my second equation? Yep.
X plus 5 plus 10 equals 4y.
Perfect. Why do we know that? Do you remember what those are called? Caitlin? Vertical angles. So if 2 angles are across from each other, they form that X shape. They're vertical angles. So my second equation, 4y equals x plus y plus 10. Okay. Do we want to substitute or do we want to eliminate? Anybody have a preference? Well, I eliminated last class, so let's substitute this time. I'm going to pick a variable. I'm going to pick x to isolate in this equation over here. So let's subtract y. Let's subtract 10 from both sides to get 3y minus 10 equals x. Then I'm going to substitute this in. 4y plus 2 times 3y minus 10 equals 180. I can combine my like terms. I'm simplifying. I'm going to add 20 to both sides, addition property. Oops. Divide by 10, division property, y equals, not 200, 20. Substitution, plug it back into one of my original equations. Let's plug it in over here to this one. 3 times y minus 10 equals x, which is 60 minus 10 equals x. Simplify, x is 50. All right, any questions on that? We're okay?